All right, so we just determined the fact that the, um, the mantle is divided into two parts. The lower mantle, which is very rocky, very rigid, and the upper mantle, which is I hate saying this, the asthenosphere. All right, the asthenosphere. And above that, by the way, is what's called the lithosphere. Then the lithosphere includes the crust of the Earth. So the lithosphere goes down to about 100 kilometers. The asthenosphere goes down to, the layer is about 700 kilometers below the surface of the Earth. These are average numbers. And then, of course, the mantle ends at about 2,900 kilometers below the surface, and that's where the outer core is. And then, you're about just under, to get to the center of the Earth. It's just about 6,400 kilometers. All right, so that's quite a ways into the Earth. I mean, this is not to scale at all. You can see, all right. I mean, these are divided into hundreds. These are thousands down here. So it wouldn't fit on the page. This goes way down. All right. So that's the main thing here. Of course, is the mantle for right now. So the upper mantle has this more plastics. I'll try to say it again. The asthenosphere. All right, and then the lithosphere is above that. The lithosphere, again, it says it. Where does it say? It's somewhere along here. Well, it's the lithosphere. The lithosphere is, it's actually extremely rigid, and it's broken up into these plates, which is really the subject of this entire chapter, or we're getting towards that. And those plates are those are the plates for the plate in plate tectonics. All right, so we'll get to that shortly. So the lower part of the mantle is the asthenosphere. Actually, the lower part of the upper part of the, oh man. All right, so included in the mantle is the part of the lithosphere. Anyhow, just part of it, because above that, the lithosphere includes the crust. They're kind of overlapping here a little bit. So the main thing here is the asthenosphere is solid, but it behaves like a plastic. And so there is this flow that goes on. The constant flowing motion of the asthenosphere greatly affects the surface features of the crust, right? Like, for example, where the mountains are, where the oceans are going to be, or, where the oceans are, not where they're going to be. Well, actually, I take that back. It does have to do with where they're going to be. As we get towards the end of the chapter, we're going to find that things are going to change over geological time, right? That the Atlantic Ocean is not constant. The Pacific Ocean is not, where it currently is. The oceans are going to change. All right. So, all right. The upper mantle has two zones. The asthenosphere. I don't know why I can't say that very well. The asthenos. I've never been able to say that very well. And the lithosphere. The lithosphere, of course, includes the upper part of the mantle and the crust. The lithosphere is cool and rigid. It doesn't flow easily. It's the other thing that's important about it is it's less dense. In fact, that it basically floats on the asthenosphere, which is more dense. So, all right, just like if you put, I mean, I'll remind you of this again probably. If you added oil and water, let's say you put water and you mix some oil onto it, the oil always floats on the water because the oil is less dense than the water, right? So the lithosphere is on the asthenosphere. All right. Because of the brittle nature, it is broken up into individual plates, as I was just mentioning. The movement of these plates is that's the cause for earthquakes and volcanic activity and the deformation of the rocks, right? Like we talked about in chapter 20 about the metamorphic rocks, right? That can take that do take place all over the earth. All right, so we're going to get much more into this plate tectonics, right? The lower mantle extends from a depth of 700 kilometers to 2,900 kilometers. It doesn't say that here, but that's what it does. And so that's the outer part of the core. Goes all the way to the outer part of the core. That's quite a bit of volume when you think about it, right? I mean, so the lower mantle is under great pressure, and makes it seems it's much more solid than the asthenosphere. All right. So keep in mind the whole thing that I just mentioned, the oil on added to water, right? Oil will always float on water because it's less dense, just like the continental crust always floats on the it'll float higher. This is actually it'll float higher than the ocean crust, right? The continental crust, which is made primarily of, you guessed it, granite. I hope you remembered that. And then the ocean crust, which is made of, you hopefully remember that, basalt, right? The basalt is slightly more dense than the granite, and so the entire continental crust will ride above the generally it'll ride above where the bottom of the ocean is, right? Where the crust that at the bottom of the ocean, which is of course always made of basalt. All right. All right. And what else do I have to say? So two distinct regions: the ocean crust and the continental crust. Oh, so the ocean crust is on average, and that's important. Is on average has a thickness of about 10 kilometers, where the continental crust has a thickness anywhere from 20 kilometers to about 60 kilometers. And so it can go much further down and even pass underneath the ocean crust. But it's still riding on top of the mantle. The mantle is much more dense, all right, so Isostates, sorry, Isostates. No, I didn't say that. I can't say this now. Isostates. All right, is just means it's just this balance, right? This remember isosceles triangles, for example, are equal. The sides of an isosceles triangle are equal. It just is. There's an equality that's going on, right? There's an equilibrium, if you will, and so there's always the downward force of gravity. So let's look back at this. Let's take this continental crust. So whoops, I did it the wrong way. This isostasty. I can't say it. I'm sorry. So this equilibrium, I prefer equilibrium. So you have the downward force of gravity, but there's also a buoyant force, and the buoyant force comes from whatever's underneath, right? So the more dense mantle is the buoyant force for the continents, of course for the ocean crust as well. So the low density crust floats on the denser mantle, right? That's the point. Um, let's see. Do I have the picture of the ship? So why are the continents so high and the ocean so low? So the this equilibrium. So you have variations of the surface elevation that result from variations in the thickness of the crust of the we're talking about the continental crust here. The areas of continental crust that stand higher than the areas of the ocean crust because continental crust is thicker and less dense. All right, so let's see. Do they show the? They don't. I'll show you a picture of this in just a second. So the Earth's crust is thicker beneath a mountain because let's read all these and we'll figure out which one it is. The roots of the mountain are heavier. No, that doesn't sound right. The mountain sinks until the upward buoyant force balances the downward force of gravity. That sounds right. The mantle rock is weak. No, it's not that. The ocean crust is thin. I mean that's true. The ocean's crust is thin, but the reason so the Earth's crust is thicker beneath the mountains because the mountain sinks the mountain sinks until the upward buoyant force balances the downward force of gravity. All right, so they don't have a picture of the. Here, we'll get to this in just a second. All right, hold on. Let's see how much time we have left. All right, so this is this is something that's been understood since Greek times. There was a guy named Archimedes that actually discovered this. Anyhow, there's always a buoyant force. If you have something that's put into a liquid, the liquid gives a buoyant force. So that's an upward force. And of course, there's always the downward force of gravity. And if you ever go to the beach and reach underneath the water and pick up a rock or something like that, and then once you take the rock out of the ocean, it always feels heavier, right? Because while it's underneath the ocean, it always has a buoyant force, and as long as it's underneath the surface, it has a buoyant force pushing it up. Let me see. What's a good example? What's another good example? Excuse me. Well, that's the same, and of course that's the same reason. I know I mentioned this before, that oil will float on vinegar, right? Oil will float on water, right? Because there's a buoyant force because the oil is less dense than water, and so the oil will sit on top, and the water has this buoyant force upward, just because of the difference in density. But that's really what it's about, is the difference in density. All right, so if you take an empty ship, it will sink to a certain level, and then there'll be an equilibrium instead of that word that we talked about earlier that I can't pronounce for some reason. Anyhow, if there's more, let's say that there's a bunch of cargo on the ship, and the ship will sink lower, but it'll sink lower, but ultimately, if it doesn't completely sink, then there is an equilibrium that is met between the buoyant force and gravity. Of course, it'll sit down further in the water, and that's the example that we're trying to show with the continental crust. All right. Well, in the next one, we'll get into this the continental drift. This guy Wigner came up with it, but here, let's go back to this picture right here. All right, so here, let me return. So this is just in the last few seconds. That's why this thing sits below further, right? This continental crust, right? It goes further down into the mantle, and so the buoyant force is balanced by gravity, right? So